Okay, we'll go to an example. If we have an inclined plate with theta and there's a gravity flow, and first we know that pressure here is open to atmosphere, pressure is open to atmosphere, so we can state that is changing the pressure in x direction is equal to 0. Yes, it is valid, except if you are changing in the area here. For example, plate is going like this. So no, the pressure can, yeah, here 0, here more, here less. So the pressure is changing in x direction, yet at the boundary condition is 0. Yes. So we cannot use, we can approximate that is del b by del x is equal 0 for this case only. But we're not going to use this understanding, but we're going to prove it, but later on we can use it. Okay. Now we can state a steady state incompressible. Steady state incompressible, that means there's no change in the time. Yes, we know that the velocity will not change in the time, yes, but acceleration can change. Okay. And it is incompressible, which is mean rho is not going to change, which is mean we can put it outside del. It is 2D flow, which is mean very big plate, so there's no velocity in z direction, and we don't have z at all, so any change in z direction is equal to 0. It is fully developed, which is mean from laminar to transient it is finished. It is fully developed, which is mean there is no change in the x direction in the velocities, which is mean del u or del v or del w, whatever, by del x is equal to 0. Okay. Now, by the way, by this term and this term, we can state that it's a flow in one direction, but we're not going to use that understanding. We're going to prove it, but later on we can use it. So right now your stock equation, or del u by del t, etc. till the end, because or outside because it is incompressible. Anything by del t, 0. We know that any change in x direction is 0. Keep this one for now. We know there is no w. We know there is no change in x. We know there's nothing named z direction. Okay, here. Why here we can say it in 0? This means the velocity, there's no vertical velocity, only in one direction. By logic, yes. Yeah, because it is 2D flow and there's no change here. So yeah, but let's plug the number. Put the continuity equation. Del u by del x plus del v by del y plus del w by del z. It's incompressible, so or outside by 0 is equal 0. We know there's no z equal 0. And we know there's no change in x because it's fully developed, it's equal 0. So del v by del y is equal 0. So the rate of change of v to y is equal 0. But remember, so by anyhow, till now, we didn't reach anything yet. Remember that because also del v by del x fully developed is equal 0. And we know we don't have even z direction, which is there's no change in the z direction, so equals 0. So we can say very clearly dv by dy equals 0. If dv by dy equals 0, and I know dy is impossible to be 0, which is mean v is equal to 0. So flow is in one direction. So if I have a fully developed 2D flow, the flow in one direction. Okay, that's why we can put this one at 0. Put all this together, so we'll find del b by del x equal mu del square u by del y square plus rho gx. Okay, rho gx is very simple. I have g in this direction, so if I need it with theta here, if I need it in this direction, so it will be cosine. I don't know where it is written. Okay, no problem. We'll write it later. So same concept. No, no x, no v, no z, no. Why? Because we don't have v's. So from this equation, we know that rho gy minus del b by del y is equal 0. So del b by del y equal rho g cosine theta. Y is cosine theta. So I have it here, this direction. So, and let's draw it better. know this one is theta. I know this one is down. And this one is in y direction. And this one is in x direction. So if this one is theta, which is vertical, which is here, so, and this one is a 90 degree, which is this one. So this one is down, or let's put it like this. This one is down. So I'm just putting this one here. Sorry. So this theta, but this one is full. So this one is 90 minus 90 minus theta. So it will be in y direction, cosine, and in x direction, sine. Okay, it is just uh, physics or angle analysis. Okay, okay. So now we finish. Okay, we write two equations. Now we can write the integration of each equation. So after we finish each equation, we need to make the integration of each equation. Let's try with the easiest one. We will make integration for this, but we will make integration also. But let's start with the easiest one. So dB by dy, put dy here, integration of dB, del b, it is b, integration of del y is y, but because it is partial integration, that's mean partial integration is taking any function of x as a constant, which is mean it's not plus constant, it's plus function of x, we don't know it. Okay, this is the first integration for this one. If I'm going to use integration for the second term, which is this one, so put it, I just rearranging, so del square u by del y square. Of course, because this one's more complicated, we need to keep it aside because it's 2 times. So first integration, it is du by dy. When we do integration for all of this, it's just algebra. So this one, we know it, it's not changing. Oh, sorry, we know it, it's not changing in y direction. Y, but b is changing in y direction. Yes, b is changing in y direction. But the definition of the partial derivative, which is db by del b by del x, it is the rate of a change due to in x direction, which is mean there's no any effect of y, which is mean in the integration to y, it is constant. There's no any relation. You get my point? So it is a constant. And this one is also the constant. So the first integration is the full constant multiplied by y plus f1x. It is not the same. That's why I put 1. Make another integration. It is y squared over 2 y f1x plus f2x. Okay. When we reach to this, we need to put boundary layers. Condition. Boundary layer condition, which is mean what is the pressure, what is the velocities in each point or in each area. Let's start with the velocities because velocity is straightforward always. Pressures is not straightforward. First rule number 1. If you're going to put a boundary layer, ensure that is your boundary layer which is going to put resulting with no derivative function in the f functions. For example, this f or this f, it should not have any derivative. In case of there is a derivative, there is a solution for it, but try to use boundary condition. Let's see. If I say that is at boundary condition y equals 0, y equals 0, I know the velocity is equal 0, no slip condition. And at y equal h, I know the velocity is equal to v top or capital U. Let's put it at y equals 0, u equals 0. Put in the equation y equals 0, u equals 0, so if 2x is equal 0. So one term is bye-bye. Type, let's put it at y equal h. I know u equal u. Put it h squared, etc., etc., etc. You will find here that is you have a term of del b by del x. We said it is not preferable, but this is our case. We don't have any other conditions we can use. Okay? We know from before, as I said, because there's no change in the area, and here is pressure, and here is 0 b atmosphere and b atmosphere, and there's no change in the area. We know that is the pressure never change. So d del b by del x is 0, but we know it, but we said that we're not going to depend on it. We're going to use the derivation till the end, because we need to know how we're going to solve such if in case we have a change in the areas. So we have a full equation with dB by del x. Of course, I just put the numbers, get the fx is equal what, put the fx in the equation, put it, you will have this equation. Now, the first step to solve any issues like this, you need to return back to the continuity, because we have three momentum equation and one continuity. To solve one like this, we need to, it is a standard steps or a copy-paste step. First, write a continuity equation as it is. Don't put any zeros. We know that it's very zero. Don't put it zero. Put it as it is. So we know that is del u by del x plus del v by del y equals 0. Good. Then multiply the both, of course, put this one in the opposite side. Multiply the both terms with the direction which is you don't want. So what you want? You want del sorry, del x. You want the del x. You want it. You want the rate of change of the pressure in the del x. So keep the del x, multiply by dy, dy and dy, full as a dimension. What happened here is it then makes the integration from 0 to h and from 0 to h. What did you done is you was trying to get the velocity, the rate of change of velocity in x direction, but in the entire full height, okay, or the full length. That the change in y is from 0 to h. We don't have over h, we don't have less than 0. So this is logic. Till now, it is logic. We didn't do anything. So this one should be equal to this one, because this one equal minus this one, multiply the du. If you put the integration h, for example, if this du is h, so h by h, it will return back to the same equation, okay? But we need it. Now we will tell ourselves, because we know that is v equals 0, so this term should equal 0. Agreed. And because we are going to do integration in respect to y, del x is has no any function in y, has no any parameter with y. So we can put it outside the integration. If I put it outside the integration, it will become dx. And of course, it cannot be dx itself, so it will be d by dx. Okay? Because it is gone outside the integration. Imagine it like d over d, but it is from mathematical point of view, because del x gone outside the integration, it is d by dx, which is mean, forget dx now. If you put d by dx multiply a function, it is, for example, an example. It is just for mathematic point of view. If I write v, for example, if I want to make a derivative for this one, we are saying that multiplied by, which is will become equal dv by dx. So that derivative, how we got it? So the function multiplied by d over dx, which is the derivative which I need to go. So this expression. Again, if you try to rearrange it based on the same concept, which is mean it will be h, dy is h, u, so d by d, so it will be again del u by del x multiplied by h, so we return back to the same equation, okay? but we needed to do this mathematical manipulation to get the exercise. Maybe you will get understand it now. If I get the exercise, then start to put the equation. Which equation? We have the equation here, and we have dx here. So put that equation here. Okay. Then make integration in y, because we said we're making integration in y. This is after the integration of y, and apply from 0 to h. It is limited integration. Okay. When you apply it from 0 to h, 0 it's everything is 0, h is everything is h. So when you plug the numbers, after the integration, y become y cube over 3, 3 multiplied by 2 is 6, etc. Simple integration. Is equal 0 multiplied by d by dx. Okay. Now, the next step of the manipulation. Start to make some algebra to put this one aside, this one aside, this one aside, this one aside, and you need take take this point in you. We need to check. We need to check, or we need to find an expression which is having only parameter, one parameter, only one parameter. This means not h cube. It's not h. You get my point. So your target is one parameter, and it's not derivative, and it is in the opposite direction, which is you are trying to get. Okay. Then now it's clear. If you're going to check, you will find here del b will not take it. So it's the full term we're not interested on. And here, yes, we are interested, but it is h cube. We're not interested on. Uh, of course, rho and g is constant. So for the fluid itself, it's not related to our problem. But here we have h multiplied by u. We need it. So put this one, multiply by the same, and put this one separate, and put it in another opposite. So will be in opposite, so minus u, u, u over 2 dh by dx. This 2 is missing, by the way. Okay, no, here is the 2, I just divided by the 2. Just some algebra. It's not a big, if you didn't divide it, it's not effect, have zero effect. And if you keep the 2 here, is no effect. So it will be minus u over 2 dh by dx. Okay. So h by dh by dx. Why we set it like this? Because keep with me. Now, make integration to x. Integration in respect to x. So this term will be as it is. This term in respect to integration to x, it will be this term. Very simple. Integration in respect to x. So x and h. H will be h because there's integration. Dx will go here. So it is very simple. Let's do it like this. Dx will go here. So dx by dx, bye-bye. Integration to h. We make integration to h. And here there is the integration to nothing, d of nothing. There's nothing going to affect. And dx, integration of dh is h plus a constant because it is total, or it is full derivative. C1. Again, I will repeat this one. Dx will go here, dx by dx. Integration of d is nothing, and integration of dh is h. Put the same equation down, plus c with c equal constant. Now, before start defining what is c, we need to ask ourselves, is h is a function of c. So now you get it, huh? We are trying to check what is the function of the void, which is, or the pipe, which is of h, or which means the area in this case, in respect to x. Is it a function or no? If it is a function, please write, for example, if I have an inclined surface and the flow is going with increasing of the area, so h will equal, for example, x, which is mean at x1 h is equal 1, at x2 h equal 2, which is mean increasing in the area. But we know that is h is constant, so we're going to keep h as it is. We're not going to write the function of x. Remember, function of x, we still have dv by del x. That is why we are trying from beginning to keep del x, okay? So you will write the equation, then put del v by del x aside, make the integration, then you will have a function of y, because you make integration in x. Put the boundary condition, you know at x equals 0, b equal atmosphere, plus rho gh cosine theta. We already know this one from here. And if you remember, we know that is b is equal this term plus function of x, and we got here b is equal this function, which is function of x, plus function of y. By anyhow, so this function of y is this one. Simple. Okay? But put the boundary condition, so b atmosphere, by the way, b atmosphere is 0, so which is equal function of y. Okay? And the vice versa. The function of x is this one. Okay? So we can write it like this. Apply at x equal L, the full length of the plate, put it, you will get C1. Okay? Of course, C1, which was here after the integration, which is this one. Okay? Which is coming from here, from the integration, which is we done it here. Put the C1 in the equation, C1 in the equation, and put the full form of the equation. Some algebra. Then you will find that is P equals 6, etc., 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 minus this one, sine theta, plus B atmosphere over G cosine theta. And if you're going to go with dv by dx, this equation, you put this one, you put this one, and you put the c, you will find that is del b by del x equals 0, because this term, if you can see, is equal to this term, but by with minus, of course, by dividing by. So this term is equal to this term with minus, so del b by del x equals 0. So we make a derivation that is pressure gradient in x, or sorry, pressure change in the rate of pressure in respect to x is equal to 0. We can use it from beginning with knowing the concept there's no change in the area cross sections, and in and out pressure is equal. Okay, now we can return back to our glorious u. Now we know that is del b by del x is equal 0, so this term is 0, this term is 0. Of course, if the cross section changes, this is a function, and this is a function, we can put it and we get the full u, but we know it is 0, 0, so it will be these terms. Okay? This example should be very easy, was no need for these steps, as we'll go direct to this one. Yet, it is good to understand. The same concept, by the way, this flow, or this concept of flow, name acute flow, which is plate is moving, fixed plate, so the flow velocity profile will be like this. There's another example. It will be very easy, very straightforward also as well. That is, we have a pressured flow, Remember, pressured flow, this means the pressure here is bigger than this one. So by anyhow, del B by del X is not equal 0, by anyhow. Okay? So even if there is no change in the cross section, we know the pressure is going to change. And there is U. This moving, we name it grid flow. The pressure flow is named Poiseuille flow. Combination, it is one like this, then sharp like this. Okay? Just how the velocity profile going to change. It is 2D flow, same, not change in C, W0, incompressible steady flow, no change in T, fully developed, which means there's no any change in X direction for U, V, and equals 0. خلاص, we know what it is because it is 2D and fully developed, so the flow is one direction. We know it. V0, W0, okay? We already proved it before, okay? We can write the same derivation for good continuity and etc. Okay. Now, the same, this is the derivation how we got V is equal 0, okay? Now put in x, so du by dt 0, 0, 0, 0. This is not 0, 0, not 0, 0, 0 because it is flat. There's no gravity in x direction. So we can have this equation. Apply in z direction. Same concept, same concept, same concept. All 0 except this 2. But there's no cosine of sine here, so it is dB by del b by del y equals this term. So it is very simple. As we agreed, we need to make integration. We'll start with the simplest one. So b equal by function of x. So just for your information, or for the information, is b is equal something plus function of x. So if you're going to think out of the box a little bit, partial derivative of b in respect to x, this 0 is a derivative of that function. Okay? Just to be in the picture, okay? Now let's return back to this one. This more complicated, put it aside. First derivative, second derivative. So first integration, second, first integration function of x. Second integration function, of course, function of x is different than this one. That's why I put 2. Function of then put 3 and y, etc. Put the first boundary condition. At y equals 0, u equals 0. You will get if 3x is equal 0. Right, nice, very nice, okay? Put in the second boundary condition, which is y equal to b, we know that the velocity is equal u. No slip condition. Y is equal to b. Sorry. Uh, it is 2b, not b over 2. I will correct it. But however, it is written here correct. 2b. Okay. So 1 over mu, but b2 square, just applying b2 square, which is equal 4 divided by 2, and here will be 2b fx, here will be divided by 2, by the way. So fx2 is equal a function of del b by del x. Of course, here it will be 2. I will correct it. So u is equal to this function. I will correct whatever it is, u, etc. Here too. Okay. So we have the function. But still, we know that this del b by del x, we don't know it. But also we know that this pressure is not changing in y direction. Sorry, pressure changing y. This del. So we have this equation. Okay. Now let's go in an approximation. If we are going to use this approximation, it will be more easy for us. But however, we can start to assume that if the pressure here is a number and the pressure here is another number, so if we assume that the change of the pressure is constant, which is mean a linear, because there is no change in the area, but an approximation, so we can know that is this one, which is del b by del x is equal constant. So we know that this one is a constant. It's just a way of approximation. It's not. So if I know the length, I know the pressure difference. So pressure difference divided by the length, so I can get the equation of u. Just a small approximation. Okay. Of course, we cannot use the same technique what we done here, because this technique is just for defining the cross sections and its relation to the edge and etc. to how much the area is going to change, which is going to affect the pressure. Now the pressure is changing only due to the friction, etc. So we need to know some other boundary condition like the pressures and some approximations which has been stated. Okay. This is another example. If we have a tube, rough tube, and here is this different tube, and this one is very big, and the water is or whatever oil is gravity flow,